Hi, I am Dr. Fousiyamol, Assistant Professor, MES College, Marampally.
Today I would like to discuss about one of the theories of coordination compound, crystal field theory, CFT. This theory is used to interpret the spectra of the complexes of D block elements. This theory involves an electrostatic approach to the bonding in complexes. It was first applied to ionic type crystalline substances. Therefore, it is very often called the crystal field theory. Crystal field theory was first developed by two scientists, Bethe and Weck, in 1930. Before starting with the crystal field theory, we have a clear idea about the spatial orientations of the various d orbitals. We know that there are 5 different d orbitals, namely dxy, dxz, dyz, dx square minus y square and dz square. 3 orbitals, namely dxy, dxz and dyz, resemble one another in producing regions of electron density in between the three Cartesian axes. The other two orbitals, namely dx square minus y square and dz square, differ from these three orbitals and also between them. The dx square minus y square orbital has the regions of electron density along the x and y axis. The dz square orbital has most of its electron density along the z axis with an annulus in the xy plane. The first three group of d orbitals, dxy, dxz and dyz. This set is referred to as T2g orbitals or T2g set. The other two group of d orbitals, namely dx square minus y square and dz square, and this set is known as Eg orbitals or Eg set. Next is assumptions of crystal field theory. Various assumptions of crystal field theory. First one is, this theory considers a complex as a combination of a central ion surrounded by other ions or molecules with the electrical dipoles called ligands. That is, the ligand has point charges or as point dipoles. Next point is that the bonding between the metal cation and the ligands arises due to the electrostatic attraction between the nucleus of the metal cation and the partial negative charge present on the ligand. That is, the bond between the metal and the ligand is purely ionic. That is, the bond between the metal and the ligand is purely ionic. Next is the interaction between the electrons of the cation and those of the ligands. That is entirely repulsive in nature. These repulsive forces are responsible for the splitting of the d orbitals of the metal cation. Next point is that the crystal field theory does not consider the overlap between the metal orbitals and ligand orbitals. Last point is that the d orbitals which are degenerate in a free metal ion have their degeneracy destroyed by the approach of the ligands during the formation of a complex. These are the various assumptions of crystal field theory. Next is crystal field splitting of d orbitals in different geometries. First one is splitting of d orbitals in octahedral complexes. The 5 d orbitals in an isolated gaseous metal ion are degenerate in nature. When a spherically symmetric field of negative charge is placed around the central metal ion, all the 5 d orbitals will be raised in energy as a result of the repulsion between the negative field and the negative electrons of the metal ion. Although they still remain degenerate, they will have a higher energy than before. This is a hypothetical situation. Considering an octahedral complex, the 6 ligands approach the central metal ion along the 3 Cartesian axes, namely from the directions minus x, x minus y, y minus z and z. Since the lobes of the two Eg orbitals, we know that the Eg orbitals are dx square minus y square and dz square. They point directly at the path of the approaching ligand. The electrons in these orbitals experience greater repulsion from the ligands than those in three T2G orbitals. T2G orbitals are dxy, dxz and dyz, whose lobes are directed in space in between the path of the approaching ligand. Hence, the energy of the Eg orbitals. What happened to the energy of the Eg orbitals? The energy of the Eg orbitals is increased, and in order to maintain the Bari center means central position, the energy of the T2G orbitals decreased. That is, the energy of the Eg orbital is increased, and in order to maintain the Bari center, the energy of the T2G orbitals is decreased. Thus, the 5d orbitals, which were originally degenerate in the free metal ion, are split into two levels under the influence of the approaching ligands. The Eg level, which is doubly degenerate, is of higher energy, and the T2G level, which is triply degenerate, is of lower energy. Here a new term is arising, that is crystal field stabilization, crystal field splitting. The splitting of the 5d orbitals into Eg and T2G energy levels by the approaching ligand is called crystal field splitting, which is the major feature of the crystal field theory. The energy difference between Eg and T2G levels is denoted by delta O or 10 dq and is called crystal field splitting energy in octahedral geometry.